Hello everybody, this is problem number 5.70 on page 264 in your book, and we have a stiff leg derrick used on ships supported by a ball and socket joint at point D and two cables BA and BC. The cables are attached to a smooth collar ring at B, which allows rotation at the derrick about the Z-axis. If the derrick supports a crate having a mass of 200 kilograms, determine the tension in the cables and the XYZ components of reaction at D. So that is what I have located on my page here. And if you notice, I've drawn my free body diagram. So all those extra chords, I'm just using them as supports. So I'm not worried about any of those. What I'm worried about is the tension in BC, tension in BA, and my reaction forces at point D. So let's go ahead and we'll be using both of these. We'll be using my dimensions here and my free body diagram here in order to solve what we're looking for. So I am going to draw my free body diagram and then my equilibrium equations. I'm also going to need my position vectors and my unit vectors in order to help solve for this. So let's go ahead and with my position vector, let's go from B to A, and then I'm going to have B to C, and then I'm going to have unit vector BA, and I'm going to have unit vector BC. So B to A, so I'm going from B up here down to point A there. So my X component is going to be positive, my Y component is going to be negative, and my Z component is going to be negative. So looking at this, my X is going to be 2 meters, which is going to be 2I minus 3J, so I'm going backwards here from the Y direction, so this is 3 meters, so it's 3J, and then from here to down to here is 6, so that's going to be 6K. So if I quickly calculated my magnitude, that's 2 squared plus 3 squared plus 6 squared, which is equal to 49, so this is equal to 7. RBC, so now we're going all the way back here. Maybe something you might want to do is stop the video, come up with your position vector, and then see if you get what I get. And what I get is negative 6I minus 3J minus 6K, which my magnitude becomes 9. If you square all those, you get 81. So my magnitude is 9. So my unit vector is going to be 2 over 7I minus 3 over 7J minus 6 over 7K. And then BC is just going to be negative 6 over 9I minus 3 over 9J minus 6 over 9K. So if you wanted to think of it this way then, if I want to look at tension BA and tension BC, I'm going to look at saying that tension TBA is multiplied by my unit vectors, which would be 27I minus 37J minus 6 over 7K. And then I have TBC, which would be negative 6 over 9I multiplying minus 3 over 9J minus 6 over 9K. Alright. So now that we have these, now we can use our equilibrium equations to solve for everything that we're looking at. So if I sum my forces in the x direction, I have dx plus 2 over 7 TBA minus 6 over 9 TBC. And that's all equal to 0. So now we're looking at my free body diagram and looking at everything in the x direction. I have my x, I have an x in the TBC, and I have an x in my TBA. So I write them all in here. If I sum my forces in the y, I have dy minus 3 over 7 TBA minus 3 over 9 TBC is all equal to 0. I can sum my forces in the z. And why am I summing my forces in the x, y, and z? Well, because I have these three reaction forces at point D that I have to solve for. So dz minus 6 over 7 TBA minus 6 over 9 TBC is all equal to, so this is 200 times 9.81, which would give me 1962. And remember, I could subtract that. It would be minus 1,962 newtons, or I just can take it to the other side right away, which would be positive 1962 newtons. Okay, now let's go ahead and sum my moment about the x-axis. If I sum my moment about the x-axis, I get 3/7 times TBA times 6 meters plus 3 over 9 times TBC times 6 meters is all equal to 1962 times 4 meters. So if you're looking at the x-axis here and you're looking at TBA right here, you have this force here of TBA of 3/7, which is going to be what? That's the y-axis. I guess I should draw it like this, which is going to cause a rotation about the x-axis. You have the weight that's causing a moment about the x-axis, which is 4 meters away. If you notice, this is 4 meters away, so my perpendicular distance is right there. And then we also had TBC, which is going to be 6 meters away, and it's going to be acting positive. Okay, and then I'm going to sum my moment about the y. And I know this is very visual and it's kind of hard to discuss it on a piece of paper, but just try and take your time, look at this, figure out how it's actually rotating about that axis. And so the last one would be 2/7 times TBA times 6 minus 6 over 9 times TBC times 6, and that's going to equal 1962, but that's going to be a negative there, times 1. Okay, so now we can look at all of our equations. I'm going to kind of scroll down here, look at all of our equations, and kind of look at what we have here. Let's just label these. In order to solve for certain things that we might be able to solve for. So here I have dx, dy, dz. Here I have TBA, TBC, TBA, TBC. So here I have two equations, two unknowns. So let's solve for these two first. So I would have 2.57 TBA plus 2.0 TBC is equal to 7848. So that's going to be equation 4. And equation 5, I come up with 1.71, doing all my mathematics there in those equations, minus 4.0 TBC is equal to 1962. Now throwing these into a matrix into my calculator, I get that TBA is equal to 2005 newtons, and TBC is equal to 1,348 newtons. So now I have my tensions in my cables. Now I have to come back in and find my reaction forces, which, and I don't think I'm going to do it here, but all I'm going to do is substitute TBA here and TBC here. I'm not going to show that work. That's simple calculation. And you get dx. Same thing for dy, and the same thing for dz. But the answers, so that way you have them here after you've done them, maybe come back and check to see if you got the same answer. I got 327 newtons. I got 1,310 newtons, and I got 4,580 newtons just by substituting these into equations 1, 2, and 3. So I think the most difficult part of these problems is actually to look at how it's rotating about an axis in the three-dimensional while it's sitting on paper. So maybe some way you can figure out how to visualize this in your brain and figure this out. If you have questions, please please throw them on the discussion page. I appreciate your time. Thank you.